my name is Cameron Burke, and this video is going to explain how to apply the nucleophilic acyl substitution mechanism to synthesis of carboxylic acid derivatives. In a previous video, I went into detail about the exact mechanism for an acid-catalyzed nucleophilic acyl substitution. This video is specifically about using a nucleophilic acyl substitution to synthesize carboxylic acid derivatives, but it's not going to cover the mechanism to quite the same degree of detail, so feel free to go back and get a refresher on the acid-catalyzed mechanism if you need to. As I mentioned in earlier videos, nucleophilic acyl substitution is cool because it can be used to create a lot of carboxylic acid derivatives, including amides, esters, and anhydrides. All of these reactions use the same typical acid-catalyzed nucleophilic acyl substitution mechanism, consisting of 4 steps: protonation, addition, elimination, and deprotonation. You're about to see those steps as they apply when you are using them to create an ester via Fischer esterification. When creating any carboxylic acid derivative, you always start with a carboxylic acid. Here, our goal is going to be to add this methanol to create an ester, using an acid catalyst. As covered in previous videos, the first step is to make the carbonyl oxygen more electrophilic in order to increase the reactivity of the carbonyl carbon. So step 1 is to protonate the carbonyl oxygen in the carboxylic acid. Protonating the carbonyl oxygen is going to result in a positively charged carboxylic acid. With a nucleophilic oxygen pulling on its electrons, the carbonyl carbon is going to be a lot more likely to react, and it's going to search out other electron sources. This brings you to step 2, addition. Now that carbon's ready to react, this is when you can add the methanol to the carbonyl carbon. Even though it doesn't have a negative charge, the methanol does have some free electrons on its oxygen, and the superelectrophilic carbonyl carbon is going to snatch those up. Then, the positively charged carbonyl oxygen is going to take the electrons from one of its double bonds with carbon, so carbon doesn't have too many bonds. As a result of the addition of the methanol to the carbonyl carbon, you're going to have to deal with this positively charged tetrahedral intermediate. It looks like this. This tetrahedral intermediate can't keep existing like this because the methanol oxygen is carrying a positive charge. But this is a proton-catalyzed reaction, so it's going to be really easy for oxygen to take back the electrons from its bond with hydrogen and kick the hydrogen off. Hydrogens are easy come, easy go in an acidic environment. This brings you to a second electrically balanced tetrahedral intermediate. As explained in detail in earlier videos, this balanced tetrahedral intermediate is temporary because one carbon is trying to support 3 oxygens, and the oxygens aren't going to want to share their electrons with such an electrophilic carbon if they don't have to. So oxygen is going to use its free electrons, and it's going to seek out a proton that's floating by, and it's going to attack it. Once the nucleophilic oxygen molecule attacks the proton, you are ready for your last tetrahedral intermediate, which sets you up for the third step, elimination. Adding a proton to this hydroxyl group created my personal favorite leaving group, which is H2O, or water as its friends know it. Anytime you create a water molecule, you should just expect that that's going to be your leaving group. Now that you've created a molecule of H2O, this oxygen is going to break its bonds with carbon, and the water molecule is essentially just going to fly away, completing the elimination step of the reaction and becoming the water that you see in your product. In the meantime, the carbonyl carbon and the carbonyl oxygen are going to reform their double bond because carbon still needs to have 4 bonds, even though its water molecule left. That means that now you're carrying a positive bond on your carbonyl oxygen. And once you have a positively charged carbonyl oxygen, you are ready for the very last step in creating an ester via acid-catalyzed nucleophilic acyl substitution. And that step is deprotonation. Just like in the addition step, hydrogens are easy come, easy go in an acid-catalyzed reaction. So oxygen is going to take back its electrons from its bond with hydrogen, and hydrogen is going to go away, and you'll be left with an electrically neutral product, and you'll have successfully turned your carboxylic acid into an ester. To recap, many carboxylic acids can be created using an acid-catalyzed nucleophilic acyl substitution. This video showed you a Fischer esterification, but this mechanism also applies to amides and anhydrides. Thanks for watching!